Okay, so it's 6 o'clock on the dot, so we'll get started. So thank you for joining us this evening for our 18th session of the Journey Down the Clackamas. So I'm Dave Bugney, a board member of the Clackamas River Basin Council. And joining me tonight is Todd Bartlett. He's the Clackamas River Basin Council's incoming board chair, and he'll assist me in the technical aspects of all of this. So before we get into our program, I'd like to cover a few items. The Clackamas River Basin Council is celebrating its 25th anniversary. Since its founding in 1996, the CRBC has worked as a non-governmental group of stakeholders to protect and improve the Clackamas River Basin and its tributaries. Their mission is to foster partnerships for clean water and to improve fish and wildlife habitat and the quality of life for all those who live, work, and recreate in the Clackamas River watershed. On behalf of the Basin Council, I'd like to thank our two gold sponsors, the Oregon Beverage Recycling Cooperative and the Clackamas Water Environment Services. So Todd's going to bring up a brief 1-minute video that describes some of the recycling or some of the services the Recycling Cooperative does. So roll them, Todd.
Well, I'm having a little technical problem here.
And that's okay. I could just keep rolling and we'll just do it the next time.
Let's see if we got it running. No, it says it's not available.
Okay, well that's no problem. I'll go ahead then and just resume, and we'll just check it off and put it on the next one. So we also like to thank our bronze sponsors tonight. That's the Clackamas River Water Providers, the Geological Society of the Oregon Country, Port Blakely, and Metro. We also like to thank the many individuals who've donated to support this conference, and we continue to seek additional donations, which are tax deductible. So the Clackamas River Basin has been occupied by Native peoples for millennia. It was originally the territory of the Clackamas, Chinook, Molalla, Kalapuya, and other peoples, and is currently recognized as lands of the Confederated Tribes of the Grand Ronde, the Confederated Tribes of the Warm Springs, and belongs to other Native peoples who may not be federally recognized. So we thank those who came before us for their stewardship of these lands and waters, and those who continue to steward them now and in the future. So we're gathered for this journey down the Clackamas to learn in-depth information about the basin and its connections to Oregon as a whole, connect with each other so that we can support our mutual efforts to protect and improve the Clackamas River and its tributaries, and have a little educational fun. So CRBC is partnering with the Environmental Learning Center at Clackamas Community College, and workshop attendees will receive a science certificate of completion for each session. If you'd like a certificate of completion, add your contact information to our Journey Down the Clackamas Conferencing Networking Google Sheet and indicate you'd like a certificate in the G column, and we'll forward your contact information to Clackamas Community College. So before we start, I'd like to share a few ground rules before we introduce our special guest. Please keep your microphones on mute unless invited to participate. And you can keep your cameras off if you like. That'll help us save bandwidth for our presenters and greatly reduce the carbon footprint of our meeting. We'll have one presenter this evening with a brief question and answer after the presentation, but Patrick Edwards, our presenter, would like you to respond at the beginning of the presentation, and he'll let you know when with some input he'd like to have from you. So just kind of keep that in mind. So please type your questions in the chat toward the end there, and we'll select questions from there. Feel free to send direct chats to friends you're seeing in the participants list. So now we'll start our presentation for this evening, and please remember again to type your questions in chat. But again, Patrick will ask those that are interested to respond up front for a it's hard to say, specific question he has. Keep yourself muted and we'll answer questions at the end of the presentation. The webinar will extend till about 6:45 tonight with questions afterwards. So our brief intro. Patrick Edwards is a senior instructor in the Environmental Science and Management Department at Portland State University and director of the Environmental Professional Program. His current research is focused on macroinvertebrate indicators of stream sediment and the effect of ecological restoration on aquatic communities. Patrick received his BS in Environmental Analysis and Planning from Frostburg State University and his MS and PhD from Portland State University. So now please let's welcome Patrick as he presents about stream food webs and energetics in the Clackamas River. Take it away, Patrick.
Thanks, David. Honored to be here and appreciate the invite, and excited to share some information about food webs and energetics in the Clackamas River to you. What I'd like to do first is I'd like to ask the group to put in the chat Are we seeing my presentation correctly?
Yes, it looks
Okay,
great.
right. If the participants, just for fun, put in the chat, what is the most important ecosystem services? What is the most important ecosystem service that you think is provided by the Clackamas River? I just want to know your opinion on which of the ecosystem services are most important to you. If you just take one moment to write that in the chat, that would be great. Wildlife conservation, good. Yeah, interesting. Salmon and trout, steelhead, yeah. Drinking water. Hi, Hannah. Anyone else want to add to that? Fish, good, lots of fish, water, good. What about recreational opportunities?
Yeah.
Oh, good, there's a recreation, good, yeah, Liz, recreation. Me too, I love recreating on the Clackamas River. I've spent a lot of time on that river, done a lot of fishing, not too much catching, but I really enjoy spending time on that river, and I think most other people do. And what I'd like to point out here at the beginning of my talk is most of the ecosystem services that you're interested in are related to the food webs and the energy dynamics in the Clackamas system. And we're going to talk about that today. I'm going to start by giving you some basic information about stream food webs, and then I'm going to move to thinking about the energy and streams and the energy in the Clackamas system. And then I'm going to wrap up with how humans can affect those relationships between stream food webs and the energy in the system. All right, and I think it's important for me to mention that I'm primarily a teaching faculty at Portland State University. I do a lot of teaching there, and I do a lot of teaching at the high school level. And so I think maybe that you'll kind of recognize that in how I give my presentation. Sometimes it's hard for me not to ask questions to the group. Okay, so today just going to cover stream food webs and energetics in the Clackamas River. Let's just start off with some basic stuff. And I think almost everyone is familiar with this, but we all know that a food web is simply who eats whom in the ecosystem. So we all know that critters eat other critters, and some critters eat organic material, and some critters eat decaying material, and we have names for those critters. So we have what are called heterotrophs and autotrophs. Heterotrophs are organisms that feed on organic material that's already been produced by the autotrophs. So we're probably familiar with this trophic pyramid, where you've got lots and lots of plants supporting the herbivores, which support the primary predators and which support the secondary predators in the ecosystem. And the reason it's shaped like a pyramid is because it's trying to imply that it takes a whole bunch of autotrophs to support the top of this food pyramid. And I think pretty much almost everyone is very, very familiar with this concept. Let's take a look at this though in streams. When we're talking about the food web in streams, we often base the food web on something called functional feeding groups or feeding strategies. So those are the scrapers and the shredders and the collectors and the predators we're going to talk about here in a second. The food web in a stream system, the base of the food web is either derived from the algae in the system or from leaves that fall into the system. So we're going to talk about that here in the next couple of slides. So let's think first about leaves as a food source. I think leaves are very interesting and often very interesting to students. So when a leaf falls into the stream, it's actually colonized by these microbes. So you have fungus and bacteria that colonize these leaves. And the fungus and bacteria are trying to get at the carbon that's in that leaf. Well, when the insect feeds on the leaf, it's not actually trying to eat the leaf itself. It's trying to get at the microbes that have colonized that leaf. So when you look down and you see a leaf, and this is true on the terrestrial land and also in water, and you see these little holes in the leaf, that's where an insect has chewed, or some other invertebrate has chewed that hole in that leaf to get at the microbes and fungus that are growing there. And I like to use the analogy with my students that it's kind of like a peanut butter and a cracker. The peanut butter is the high nutritious part the microbes and the fungus. And the cracker is the leaf that's simply the delivery mechanism. So this is an important functional process in streams, because what would happen if these leaves were not colonized by fungus and bacteria? The leaves would never be broken down and we would be buried in leaves. So this is a really important process in the base of the food web. It's the detritivore part of a food web. So we have this organic material that's being consumed by the invertebrates and breaking down the size of that particle. The other part of the food web is the algae. So I think everyone's probably had this experience when you're walking in a2 it's very slippery and it's hard to walk on the rocks, and that's because they're covered in algae. And there's two main types of algae on the rocks that grow here, and it's on the top of the rocks, and we call that periphyton. So periphyton is a term we use to describe the algae and the diatoms that are growing on the surface of the rocks. And we have soft algae, and then we have diatoms. And soft algae is important, but diatoms are a really interesting part of the food web and streams, and we'll talk about that more here in a second. If you take a close look at the diatom community on a rock, you will see an amazingly diverse community. And the first time I saw this, and the first time I started working with diatoms, it really just excited me and kind of blew my mind. I had no idea that the diatom community on rocks was so complex. And you can see you've got all these different types of diatoms growing on the rocks, and some of them are quite large and some of them are quite small. And diatoms are basically single-celled autotrophic organisms that you're probably familiar with. They create this silica shell that produce these kind of beautiful structures. They're in the oceans. You've seen the radial type that are so beautiful with the symmetry. And those are the same group of organisms that are living on top of the rocks. And they turn out to be a very nutritious food source. So here on the left, you can see this diatom with the silica skeleton. And diatoms store their energy as lipids, which is kind of interesting because that lipid is the omega-3 fatty acids that everyone is interested in fish. And my advisor, did someone have a question? Oh, sorry. My advisor told me this when I was working on my PhD, Dr. Pan. He said that fish smell like diatoms. And I thought about that a second, and that's such a profound statement if you think about it. Here we have a food web system that is concentrating this very valuable biomolecule that is very nutritious, and it's moving all the way up through the food web and being stored in the fish. And if you're ever on a stream one day, pick up a rock that's nice and slimy, rub your hands all over it, and then smell your hands. And sure enough, it will smell exactly like a fish. And to me, that just was such an interesting part of the food web that never occurred to me before I started working on this stuff. Okay, so if you think about the base of the food web, what you'll realize is that the canopy is very, very important to which aspect of the food web is the primary source of energy in the streams. So with a small stream and a closed canopy, you're going to get about 98% in some streams, about 98% of the energy is derived from leaves that fall into the stream. And that's because for two reasons. One, you've got a lot of leaf material falling into the stream, but two, you've got a lot of shading and you don't have a lot of primary production because the sunlight is not penetrating down to the bottom of the stream. As you move downstream and the canopy opens up, you begin to get more primary production because the sunlight is penetrating to the bottom of the stream. The algae are using that sunlight to produce biomass, and there's not as many leaves falling in the stream because the canopy is not arching over the stream. So the canopy is very, very important for which source of energy you'll find in a particular stream. So let's go back to this food web and go into a little bit more detail, look at a little more detail about some of these aspects of these feeding communities that I think are quite interesting. And we'll start with shredders because basically those are shredders are the organisms that you'll find up in the upper reaches of the watershed where the canopy is heavily closed and you got lots of leaves in the stream. So there's a very well-known shredder in Oregon streams. It's called the Pacific giant stonefly, and that's the stonefly here on the left. It can be 2 to 3 inches long. It is quite a big stonefly, and students really get excited when they see it. And they often get more excited when they learn that this huge stonefly, this big stonefly, is basically a vegetarian. It eats leaves. And it has these incredible mouth structures here to grind up the leaf and get at that fungus and that bacteria growing on the leaf. And then it has these other interesting feeding structures that move those particles into their mouth. So these insects and a lot of the other invertebrates have these specialized mouth parts for consuming this organic material. So here is that leaf picture I showed you before with the holes in the leaves. Crayfish, you may not realize, will actually also eat some leaves. Their crayfish are pretty omnivorous critters. We think of them as predators, but actually they actually eat a lot of leaves and getting at that fungus and bacteria, just as the other invertebrates are. This is a cool one. I like this one because this is an isopod. It's a doodlebug, just like you see in your yard, or some people call them a roly-poly. And again, this critter will be chewing up those leaves and breaking those leaves down into smaller particle sizes. Now, what's fascinating about these insects is that their life cycles are highly tuned into the leaf fall that occurs every autumn. So I just want to draw your attention here. This is shredders, number of insects per square foot. I know it's the English measurements, but it's often easier for me to conceptualize sizes in English measurements. So I'm going to stick with feet in this presentation. But notice here, every fall, a peak of these little brown stoneflies that are shredders, and they're feeding on all the leaves that are falling in the stream, and they're completing their life cycle and emerging as adults. Sometime late in the fall, they lay their eggs, and in the spring, they're very, very small. They're not really feeding on leaves, they're feeding on other bits of organic material. But as those leaves fall into the stream and become a very nutritious source of energy, those stoneflies get really, really big and very, very abundant and are growing on that energy provided by the fungus and bacteria on the leaf. I really like this graph here because one, it shows such a nice regular pattern, but you can also see, if you look carefully, this kind of long-term variability in the insect populations that's probably related to some broad-scale climatic factor that is driving both maybe leaf production, but probably more likely the conditions in the stream related to temperature and precipitation. Now let's move over to the scrapers. Scrapers are called scrapers because the term is describing how the insects and invertebrates and also some of the fish feed on the algae. So scrapers, if you remember looking at that, if you remember the scanning electron microscope image I showed you of the diatom community on a rock, you notice it's a highly diverse community. And mayflies in particular, but lots of other invertebrates too, have developed this amazing, these amazing mouthpart structures for harvesting this really nutritious diatom that's growing on these rocks. And when I first realized this, I really got interested in the relationship between how insects feed and diatoms and the effect of pollution on the diatoms, and then subsequently how well insects could feed on those diatoms. And I really like this picture. This is from a paper in 1989. This is a very common mayfly in streams, and you can see this mandible over here has been modified into this almost blade-like structure. And this mayfly crawls along the top of the rock and sweeps those brushes over the algae and over the diatoms and cuts down the algae and sweeps up the diatoms and then ingests them, and has other mouth parts that moves that material into the insect's mouth. And you can see here, this is just quite fascinating. When you really zoom in and look at these structures, they have all these like little cutting blades that they use to harvest those diatoms. And if you notice here on the bottom, this is what happens as the blades wear out and the feeding efficiency of the mayfly goes down as those blades wear out. And then when the mayfly molts and gets bigger and sheds its old exoskeleton and has a new exoskeleton, all of these blades are replaced, and the feeding efficiency of that mayfly is back to normal again and increases. Quite fascinating stuff. When you see a snail and you look closely at a snail's mouth, it has these very hard structures that are kind of like teeth. They call them radula, for rasping up and scraping up the algae. And they do a very good job at feeding on diatoms and algae on top of the rocks. This mayfly over here has this really interesting structure. It doesn't scrape algae. What it actually does is it gouges it up. It has this kind of pick-like, shovel-like mouth feature, mouth part that pries up the algae. And then you can see this. I love these little brushes over here that the insect uses to move those particles into their mouth. It's just quite fascinating assemblage of tools that insects use to get at these diatoms, because the diatoms are so rich and nutritious. And if you look at long-term data for mayflies, you'll see kind of a similar thing. The pattern is not as clear as the shredders, but here you can see this mayfly has, their peaks are in the spring. Here's another kind of peak between these two falls, and here's a nice peak and a peak and a peak and a peak and a peak. And what's going on there is that the insects, the mayflies, are harvesting that new growth of diatoms in the spring. So kind of very nutritious, kind of like the green buds of plants that deer like to feed on. They're feeding on this new growth of diatoms, and they are, their life cycle is synced up to accessing that nutritious source of new diatoms in the spring. Now let's move over to the collectors. Now the collectors are interesting because the collectors are really organisms that are feeding on the organic material that has broken down in terms of the physical size. So the reason why these two arrows here are orange is because it represents the physical breakdown of the algae and the leaves. And just like the scrapers and the shredders, collectors have all kinds of interesting strategies for access and utilizing this organic material in the streams. So now we're going to move up into some of the other critters you may be interested in, and some of the fish and some of the non-insect invertebrates. So over here you have what is kind of like a freshwater shrimp. We call it a scud. They crawl around on the bottom of the stream and consume kind of larger particles of organic material. And it's important to recognize that we categorize collectors as either, we categorize collectors based on the size of the particle that they eat. So these large scale suckers that we often catch in the Clackamas River are feeding on all those large particles of organic matter. They're actually not feeding, as far as I know, they're actually not feeding very much on the algae. They're really looking for organic matter in terms of large sized particles. We have several mayflies, this is amylated mayfly, that crawl around on the bottom and picking up with their mouth parts and also their legs pieces of organic material and feeding on it. And then we have a true fly. This is a crane fly that you're probably familiar with. They often see crane flies in your house. They end up in your bathroom for some reason. They're the true flies with the really big wings. Sometimes people call them mosquito hawks or mosquito eaters. And those are the ones that live in streams, are also eating large particles of organic material. And these crane fly, Tepulidae, you're probably more familiar with them because they cause problems with your lawn for the ones that live in soils They can often be a pest, particularly on golf courses. But the ones that live in the stream, of course, are feeding on these large particles of organic material, and very important part of the food web. As we get down to the smaller particles, and what we're talking about here is very, very fine organic material, smaller than a pinhead, very, very small, and oftentimes floating in the water column. And the critters have developed all kinds of interesting strategies for accessing this material in the water. So this is another true fly. It has these fans on its head that it waves in the water. And as organic material sticks to those fans, it will run the fans through its mouth and get the organic material off. One of my favorite collectors is the net spinning caddisfly. This is a web this insect weaves underwater, which is quite fascinating. They take these needles and organic material and they secrete a silk, very similar to the silk secreted by spiders. And they weave these really intricate webs on the bottom of the stream. And as the water flows through those webs, the organic material and sometimes little meiofauna are caught on that web. And the caddisfly just cleans off that web and pulls that organic material off and feeds on it. And there's all kinds of interesting studies that show that these caddisflies will change the size of their mesh depending on what kind of material they're trying to harvest or where they are in the current. In strong currents, they tend to weave larger size nets, and smaller currents, they tend to weave finer nets. So just this amazing strategy for capturing organic material in flowing water. I think we're probably all familiar with limpids and the clams that live in the Clackamas system. And those are filter feeders. They're moving water through their bodies and collecting that organic material. And you may not know that lamprey in their juvenile stage are filter feeders. So they live in the soft sediments and filter water through their mouths and feed on organic material. And now we're going to move up to predators. So I think everyone is kind of familiar with the celebrated rainbow trout and the steelhead predators in our system, and the salmon smolt that predate in our system. But there's some other really interesting critters that live in streams that are predators. So this is a damselfly, and I love this image. This is a friend of mine, Jeff Adams, took this picture. And this is the lower jaw of a damselfly, and it extends maybe 20 or 30% of its body length out into the water. And it quickly projects that lower jaw out and grabs a hold of little fish, small minnows, and probably some insects as well, and pulls them into their mouth to feed on them. You may have seen these little sculpins in the stream. Those are voracious predators, the feeding on insects that live on the bottom of the stream. And we probably all know about stoneflies. Some of the stoneflies are predators here, and you can see this stonefly. This is a yellow stonefly, has caught this poor little small minnow mayfly using these gnarly teeth structures that clasp on to insects and hold them with these teeth, and then grind them up with these other structures of their mouth, and then use these bristles to push the material into their mouth. So all kinds of interesting adaptation for predation in streams. So let's think about feeding in the Clackamas system here. And I'm gonna think about a simplified system and a continuum of how the feeding changes from the upper reaches of the watershed down into the lower reaches of the watershed. Now, I know this is a simplification of the Clackamas system, but it's useful for kind of illustrating how the organic material changes as we move down through the system. So let's start with particle size. So notice up at the top of Eagle Creek, and what we're talking about here is very, very small streams, 4 or 5 feet across at the most. So I recognize that as you move downstream, Eagle Creek gets much better. But let's think about the very small parts of Eagle Creek. And notice the particle size is very, very large. And that's because it hasn't broken down much. It's a leaf that falls into the stream. It's being consumed by the shredders. It's being broken down by the physical processes in the stream. And as that leaf or organic material gets down into the mid reaches of the Clackamas, the particle size is smaller and you have a different feeding approach to access those particles. As we continue to move down and we get into the Willamette River, the particle size is very, very small. That's because the physical processes have broken down that particle. The feeding processes have broken down that particle. And that very, very small particle size is suspended in the water column and is floating out the Willamette and then down towards the ocean. So what would we expect of the feeding community as we move down the system? Well, let's think about shredders. So it makes sense that we would have the most shredders are at the top of the headwater streams where you've got a lot of leaf inputs. We get less shredders as we move down into the middle Clackamas, and you have almost no shredders over here in the Willamette River because there's just no large particle sizes for those shredders to feed on. Now, let's think about scrapers. So in the upper reaches of Eagle Creek, those scrapers, not a lot of algae is growing because of the closed canopy. So you don't have a lot of scrapers up in the upper reaches. But as we move down into the mid Clackamas and the canopy opens up, you just have a substantial increase in the number of scrapers because you've got a lot of sunlight penetration, you got a lot of primary productivity, and a lot of feeding opportunities for scrapers. Nice large rocks that the diatoms and algae can grow, the diatoms and soft algae can grow on. Nice flowing current, bringing nutrients down to the algae. So you just have a ton of scrapers typically in the midsections of a river where the canopy's open. And then as we move down to Willamette River, because of the depth of the Willamette River, you don't get a lot of sunlight penetration down to the bottom. And because of the stability of the bottom of the Willamette River is so low, in other words, the particle sizes on the bottom of the Willamette River are so small that they don't provide a stable base for the algae to grow on. So you really don't have a lot of scrapers down in the Willamette River. Now let's take a look at collectors. So here, because collectors like to feed on kind of smaller size particles, these collectors up in the upper reaches are more than the scrapers, but less than the shredders. But notice as we move down into the mid Clackamas here, we begin to pick up more collectors. That's because the organic material particle size is the right size for them to feed on as you get down into the middle of the Clackamas system. And down here in the Willamette River, you have a bunch of collectors because there's so much organic material moving through that system and so little primary productivity, so such little algae growth, that really the only thing for the, in terms of collectors to feed on are very, very small particles. So the difference between the collectors here and here in the upper reaches and in the mid reaches is that they're feeding on generally larger particle sizes than the collectors in the Willamette River, which are feeding on very, very small, fine particles that are suspended in the water column. And they just, as I showed you before, have all kinds of interesting strategies for accessing that food. Now let's take a look at the predators. The predators in the system remain about the same. You've got predators up here in the upper reaches, you know, the rainbow trout and some of the salmon, salmon smolt, and you've got the stoneflies, and here you've got the predators down in the mid Clackamas, and then in the Willamette River you have predators as well, particularly if you include some of the invasive fish like smallmouth bass. You can actually have quite a bit of predators down in the Willamette River. But what I want you to notice here is look at the mid Clackamas. The mid Clackamas represents pretty much the most diversity in feeding, and that's important to recognize in these systems. And we're going to talk more about that here in a second. All right, now this is occurring, and I wanted to keep this simple, but this is occurring throughout the watershed. So in the upper reaches, you have pretty much the same distribution of feeding groups. And I want to point out something interesting here. I think you're probably all familiar with Rock Creek. Rock Creek is a very, very small stream that flows into the Clackamas pretty low down in the system. And this is really important because this represents kind of this like jump point in the feeding continuum, where you have this input of a whole different type of organic material than you would expect to see this low down. And one of the things this supports is kind of the diversity of feeding groups. So you would have in this down here in the lower section, a feeding group that you may not normally see because typically the streams are a little bit bigger down there. So these little streams that flow into Rock Creek in the lower reach, into the Clackamas in the lower reaches represent this kind of important jump point in terms of diversity and feeding in the Clackamas system and in all river systems. All right, so I've talked about kind of the basics of this food web, and we have the base of the food web is either driven by primary production in algae, and particularly in terms of diatoms. And then over here, you've got the leaves that fall in and they move up to the collectors. And then we've got the scrapers eating the algae and the shredders eating leaves and the predators eating everything. But this is an incomplete version of the food web. The food web really looks like this. So you've got the algae creating the insects, the algae being fed on by the insects and the leaves being fed on by the insects. The insects are converting that leaf material and that algal material into their biomass. So these invertebrates that are scrapers and shredders represent this critical transformative link in the food web because they're converting the algae and the leaves into their own biomass. And then those in turn are being fed on by the fish. But you're probably aware that the insects don't just stay in the stream. The insects emerge out as adults where they become really important food sources for spiders, bats, birds, and lizards. And there's just been all kinds of fascinating studies where they try to disconnect this relationship between the stream and the forest, and they can show it has this profound effect on the communities of insects when you don't allow the insects to get up into the canopy as they emerge, or you prevent terrestrial invertebrates from falling into the stream. And what I want to point out here is that this boundary here between the stream and the riparian zone is not a real boundary. It's a human contrived boundary. The ecosystem doesn't see a boundary there because essentially you've got this transfer of organic material and energy from the stream up into the riparian zone and from the riparian zone down into the stream. Because remember that the forest is feeding the stream with its leaf fall and also with the falling of the terrestrial invertebrates. And there's a saying that the forest feeds the stream and the stream feeds the forest. And this schematic illustrates this quite well, that these are two interdependent systems, and the ecosystem boundary really is not there from the ecosystem perspective. Now, it's often useful to simplify these systems a little bit and think about them in terms of energy and transport. So we can envision the within stream. So now I'm just talking about within stream. We can envision this cycle of nutrients and biomass that are circulating around in the stream, being uptaken and turned into biomass and then being returned back down to the bottom of the stream in terms of nitrogen and nutrients for algae production. And what's fascinating about this is because streams flow, you get this, what's called nutrient spiraling. So because we have this unidirectional flow, the nutrients and organic material, the nutrients and energy really in particular, flow down the stream in this kind of spiral pattern, being absorbed by the algae and then released back up into the insect biomass and then returned back into the algae as that material moves downstream. And we often, as scientists, think about the spiral in terms of its length. So a really, really long spiral indicates that the nutrients in the system take a long time to move up into the food web and back down into the algae and down into the base of the food web. A very tight spiral means that that is occurring very rapidly, and you've got a very productive system because the nutrients that are released are quickly uptaken, moved up into the biology of the system, and then as those organisms excrete waste, or as they die and decompose, the nutrients are captured by the algae, and then the feeding of the algae returns those back up into the spiral. Now let's think about this for a second. If the stream is constantly moving nutrients downstream, why aren't the rivers devoid of energy? Why isn't it all just flushed out? Well, we have critters that return back to the system upstream. And I think everyone knows this is probably, this is salmon. So I think everyone probably recognizes the importance of salmon returning and bringing those nutrients back into the system so that they can be used again and transported downstream. And I'm sure everyone is aware of the stable isotope studies, where you can find marine derived nitrogen in the leaves of trees alongside of the stream, because those salmon are bringing up that nitrogen and those nutrients and dying in the stream and releasing those. But something you're probably not aware of, which I think is interesting, is if you're ever sitting on a stream and watching a hatch of insects, notice which direction they fly. They typically fly upstream. Now, this is mostly because in the evenings you have a kind of an upstream airflow in river systems, but they also intentionally fly upstream to lay their eggs. So not only is it the salmon that are returning upstream, but it's also the insects that are flying upstream to lay their eggs. All right. Now, let's go back and think about this trophic pyramid that we're all familiar with. So what this shows here is at the bottom, you've got a lot of phytoplankton supporting all of these critters that are feeding on the phytoplankton, and these critters are feeding on these critters, and you've got this very small amount of predators that are supported by a ton of primary producers. Well, it turns out that the trophic structure of pyramids is actually inverted. And this is fascinating. It doesn't take one way to interpret this is it doesn't take a whole lot of algae to support the salmon secondary predators in a stream. And the reason why is really has to do with algae. It's quite fascinating. Algae, first of all, have a very high turnover rate. So they're constantly growing, reproducing, dying, and continuing to create biomass year round. So they have a very high turnover rate. The other interesting fact about algae, that's particularly diatoms, is that they respond positively to feeding. So when algae are eaten by other insects, when they're scraped and the rocks are rubbed and scraped by the algae, by the scrapers, it actually stimulates algal growth. So you just have this very productive base of the food web with a very important lipid oil being generated and moving up through the food web. It's a very nutritious biosubstance. It causes this inverted pyramid. Plus, as we're all probably aware, the salmon returning back into the system represent a ton of energy and biomass. So we were talking at the beginning of the day today about how many salmon have returned this year into the Clackamas. And if you think about and watch salmon return, there can be thousands and tens of thousands and hundreds of thousands of salmon returning into these systems and causing this inverted trophic structure, which is mostly unique is a mostly unique ecosystem. It turns out that marine systems actually have a similar inverted pyramid. All right, so let's think about the system the Clackamas system in terms of its energy. So we're going to look at spiral length, then we're going to look at the complexity of the food web, and then we're going to look at primary production again in terms of algae, and then we're going to look at something called the energy balance. And this P to R means the ratio of production to respiration. So let me just explain that a little bit. We all know what production is. That's when autotrophs use the sunlight to create biomass. Respiration occurs when heterotrophs feed on organic material and incorporate that into their biomass. So productive systems, algae-based systems, are producing energy essentially, and heterotrophic systems are losing energy, but they're increasing their biomass. So let's look at what happens with spiral length first. So up at the top of the watershed in these very small streams of fast flowing water, the spiral length is very, very long. So the material is transported, the nutrients are transported far downstream before they're reincorporated into the algae biomass. Look what happens here in the mid-Clackamas. The spiral length shortens substantially. And that's because there's so much productivity. Those nutrients are rapidly uptaken as soon as they're released. So you have a very, very short spiral length in the mid-Clackamas. And then when you get back out to the Willamette River, you get a real long spiral again. That's simply because there's just not a lot of productivity going on in that system. There's a lot of heterotrophy going on in that system, all those collectors eating those fine particles. Let's look at the trophic structure. So up here in the upper reaches of the headwater, you have a more simple trophic structure. You pretty much have just the leaves falling into the stream and then the shredders and then the predators. But if you move, when you move down in the mid-Clackamas, that trophic structure gets a little more sophisticated and longer because you've got algal production, you've got heterotrophy, you've got the predators, and you could have some secondary predators. So you got insect predators and you've got fish predators. And then when you move down into the Willamette River, you still have a long food web just because of all the predation by fish down there. Let's take a look at primary production. I'm sure you already recognize what this is going to look like. Here in the middle, of course, we've got the highest productivity. And over here, we've got much lower because of the shading. And then as we talked about, the depth and the stability of the substrate lowers the primary production as we move down into the Willamette River. Now let's think about the energy balance. Up in the headwater streams, heterotrophic, detritivore driven, eating lots of organic material, incorporating that organic material into their biomass, and that's basically a net energy sink. But we move down into the mid reaches because of all this primary productivity, you get a ton of productivity. And essentially that system is, the ratio of energy balance is positive. And then when you get down into the Willamette River, again, because of the heterotrophy and the lack of production, the energy balance drops back down to negative. But I just want to point something out. Notice again, the mid-Clackamas, the middle of the system has the most diversity of those of the stream energy sources. All right. And as I mentioned earlier, this is, of course, is going on all throughout the watershed. And here you can see at Rock Creek, again, jumping that kind of energy continuum by this being a little stream flowing into the lower reaches of the Clackamas. Now, let's think about what humans can do to affect these systems. So clear cutting down to the riparian zone on these headwater stream, it reduces the amount of organic leaf material that's moving into that system. Putting a dam on the Clackamas River affects that nutrient spiraling, resets the nutrient continuum, and even blocks material from getting downstream. And when you channelize streams and straighten them to speed the water flow off the, to keep the streams from flooding and to move the water quickly downstream, you lengthen that nutrient spiral because it's taking a long, the water is flowing so quickly, it's taking a long time, a lot of spatial distance for that, those nutrients to be reincorporated. And when I was working on this presentation, this made me think of something my dad used to tell me as a kid. He would say, and this is in response to me getting in trouble, he would say, it's never the main effect. It was never the main thing you did that's the problem. It was the 5 or 6 bad decisions you made before you made that mistake. So my best memory is him referring to when I wrecked our family car. And he said it wasn't the main effect of wrecking the car. It was the 4 or 5 poor decisions that you made before you wrecked the car. That's really the problem. And what my dad would say to me is that it's never the main effects, it's the interactions. And I honestly don't think I fully understood that until I was probably in my 30s or 40s. And what my dad was saying is that it's not just the activities that humans are doing on the land, it's the interaction between that activity and the natural processes in the stream that have such a huge effect. And I left this slide cluttered on purpose, because what I'm trying to illustrate is how complex these systems are, and how these changes to the system that are could be human from human activity are amplified and magnified as we move down through the system. And if we're not careful, that system can kind of lapse into some alternative stable state that's difficult to get back out and get these natural processes refunctioning again. So I'll leave you with this. Last thought here, that ecosystem services in the lower Clackamas are supported by a complex and interconnected system that is dependent on the conversion, production, transport, and return of nutrients and organic material. It is a system in which the effects of human activities don't just add up, but multiply up because of the interaction between the human impacts and the natural function of the stream ecosystem. And I point out this Rock Creek restoration here. I've been working with the Water and Environment Services folks on this project for years. And that's what they're trying to do here. They're trying to re-establish these natural processes in Rock Creek that were lost when this stream was channelized and straightened for development. So that's what this restoration work is trying to do, reestablish these natural processes. So with that note, I'd just like to take a moment to thank some folks that have worked on this. Much of this data that I showed, pretty much all of this data I showed you today, and much more that I didn't show you, was collected by my students. So we've been going out to Rock Creek and many of these stream systems for many, many years. And the students have collected this absolutely amazing data set that someday maybe I'll share with this group. I'd like to thank the funders who have supported this work, and that's Water and Environment Services, particularly Gail Shalom and Portland State University, and then the Student Watershed Research Project, which is how we kind of manage the grants that come through this program. I also want to thank my colleagues, because they have really supported me and helped me understand these processes that I just described. In particular, I just want to thank Dr. Pan, my advisor. He has pretty much taught me everything I know about ecosystems. So with that, I think we're perfect timing. We have about 10 or 15 minutes left for questions.
Well, Patrick, that was excellent.
Thank you.
Very excellent. I appreciate that. Very well put, very well explained. So now, Todd, if you wouldn't mind fielding any questions in text chat for Patrick, that would be great.
Yeah, so there aren't any questions in the chat.
Great.
So either you did a fantastic job explaining everything, and so nobody has any questions, or they've been holding off. If you'd like to unmute and ask your question, you could do that as well.
Yeah, thanks. I think everyone wants to get to the baseball game. Heat wave earlier this summer, and let's see, there was a question that just came through. Heat wave. All I can say is that I have not. So the question is, did the heat wave affect the invertebrates, macroinvertebrates? The data does not show that it did. I would need a couple more years to look at the the data in the long term. But I've been collecting my regular collecting schedule that I've been doing for almost 20 years now. I have not seen anything interesting.
How about the wildfires? What kind of effects have they had?
Again, I don't have any data for that. Wildfires are kind of tricky because some wildfires, moderate levels of wildfires actually release a lot of nutrients to the stream, and they can increase productivity. So sometimes the response of streams can be positive to wildfires. But like all systems, if there's too much intensity, fire intensity, or too frequent of fires, then it can cause a problem.
Okay. Carol asked, do diatoms actually attach to rocks?
I believe that they secrete something that allows them to stick to rocks, but they can also move. So they have these structures that allow them to move around on rocks. Some diatoms cannot move at all. Some diatoms can move very quickly and avoid all kinds of habitat conditions they don't like. And some diatoms kind of move, the middle speeds.
So there's a question about the inverted pyramid showing the algae at the bottom.
Yeah.
Is that based on mass of each trophic layer?
Yeah, it's, again, this is just a generalization and a broad scale conceptualization, but generally it's those trophic pyramids are based on either biomass or calories in the stream system.
And a fan would like to point out that you wrote the guidebook on macroinvertebrates in the Pacific Northwest.
Yeah, thank you. Who is that fan? Liz. Liz is a big fan. Yes, thanks, Liz. Yeah, the other question about the dams, this is not my area of expertise for sure, but dams are typically create a barrier to organic material transport and nutrient transport. And frequently downstream of a dam, you don't have a lot of nutrients in the water. You don't have a lot of organic material because that's trapped behind the dam. And one way you can think about dams is they reset that continuum that I showed you on that on those slides of the Clackamas system.
It's a question about, do you have any thoughts on how hatcheries affect the ecosystems, good or bad?
Yeah, I'm going to decline that question. I just don't know, honestly, and it's such a contentious question. Ben, I'm sorry, I really just don't know that much about it. I think there's all kinds of perspectives on hatcheries and ecosystems. And
Jane asked, do lamprey occur in the Clackamas? If so, how far up?
They definitely occur in the Clackamas. I'm not sure how far up. Lamprey are kind of this mysterious critter that a lot of people don't know about. It's interesting because I was actually out today collecting lamprey with the state. And lamprey can be in very urbanized streams. They can be in very degraded stream systems. So they're pretty much everywhere. They're just hard to see because they're typically buried in the sediment, and you get them out by electroshocking them very gently with this setting that's called a tickle setting. So you basically tickle them with the the electricity, and they come up out of the sediment, and then we catch them with a net.
Somebody also had a question about what is the name of your field guide? They might be interested in using it in a watershed processes class.
Yeah, stream insects, the Pacific Northwest. Drop me an email, patrick.edwards@pdx.edu. I'm easy to find, and I'll send you a copy of that. I can show you how you can get that field guide up. I can just send you a copy.
All right. And somebody said that I think the excuse me, the lamprey are in Rock Creek.
Yeah. Yeah.
And the lamprey extend all the way up into the North Fork, Eagle Creek, Clear Creek, and I believe they're even in the upper Clackamas.
Yeah.
So somebody said planting hatchery salmon carcasses is used to replace naturally dying wild salmon. Is there a way to replace naturally occurring vegetation that is reduced by clear cutting or dams?
Yeah, that Clackamas Water Environment Services is spending a lot of time and effort to replant vegetation along these restored reaches. And some of the work that Dr. Pan and I are doing is looking at the effect of restoration on diatoms, because diatoms respond to this nutrient cycling quite rapidly. They may be good indicators of restoration, the change in the nutrient dynamics associated with restoration. We're actively working on that, researching that right now in several different streams.
Todd, you might want to also mention the CRBC Shade Our Streams program, similar.
Go ahead, Dave.
Okay, so those are landowners in the lower Clackamas. that own land along creeks that feed into the lower Clackamas, you should contact the Clackamas River Basin Council to see if your property is eligible for the Shade Our Streams program, which will replant, it will kill invasive species like reed canary grass and blackberries and whatnot, and replant them with native vegetation appropriate to your vegetation zone. So it's certainly something worth considering, and it would be a no cost to you.
And we've completed over 30 miles of streamside shading in the basin.
Excellent.
But Chauncey just lobbed me a softball question. Thanks, Chauncey. Disturbance is key. And I didn't want to drift down this road too much, but it explains what's going on in the middle Clackamas in terms of the high diversity. Moderate levels of disturbance maintain the highest levels of diversity. So disturbance is critically important to streams. And I think most people don't realize that floods are good for streams. They roll over the rocks on the bottom of the stream. They reset the successional path that the diatom communities and insect communities are on. And so one of the reasons we see the highest diversity in the middle sections of the stream is because they have the moderate levels of disturbance. The upper reaches, the disturbance regime is too frequent, and the lower reaches down like in the Willamette River, the disturbance regime is too infrequent. And so my students like to call this the Goldilocks hypothesis. I think it's so funny because they're actually right on. It's the middle levels, or the not too hot porridge that the ecosystem really benefits from. And so you have to be careful about preventing disturbance in all ecosystems, because in the end, no disturbance equals low diversity.
Great.
Does that answer it, Chauncey?
Excellent job, Patrick.
Thanks for coming.
It's good talk.
Thank you.
Hey, Todd?
That's it for the questions. Several comments, Patrick, about how much people enjoyed it.
Thank you.
Some said the best ever in our series.
That's too kind. No, I don't believe that.
Truly awesome. Great presentation. So lots of affirmation coming in.
Thank you.
Your way.
It's 20 years of teaching. So.
Well, we appreciate the work over that 20 years and how you've distilled it into this presentation tonight.
Well, thank you.
Thanks, Patrick, and thank you again, Todd, for marvelously shepherding this. So the next session will be on November 16th, and we'll continue our series focusing on water and fish. We will cover anadromous fish, trout, and lamprey species within our basin, which will also be a very interesting talk. So you can use the same Zoom meeting link, and you're already registered for the event. We'll send a reminder email the day before. And just to kind of follow up on what Todd was just saying, I was checking some of the YouTube links to our previous sessions, and some of our earlier sessions, the videos have gotten over 400 views. So it's they're starting to catch on. So we'll send you a link and a thank you email with these links, as well as a link to the recording and more information about getting continuing education units from Clackamas Community College. Our thanks to Pat tonight for tonight's excellent talk. And
thanks for all the kind words from everyone. I really appreciate that.
You bet, well deserved. We also thank our gold sponsors, Oregon Beverage Recycling Cooperative and Clackamas Water Environment Services, and our bronze sponsors, the Clackamas River Water Providers, Metro, Port Blakely, and the Geological Society with the Oregon Country, who are helping us keep this conference free for everyone. And thank you for joining us tonight. So please let us know what you thought of tonight's program. Some of you already have, so thanks for that. And hopefully we'll see you 2 Tuesdays from now on November 16th.
Yeah. Thank you. Feel free to reach out. My email is easy to find if you have any questions or want to talk more about insects. And this will be a plug for a future presentation on our citizen science program that Gail Shalom and Water Environment Services has been supporting for many, many years now. It's quite fascinating.
That's a good point, Patrick, is that we'll have Patrick back on May 31st of next year. He's going to be joining us when we talk about public policy and citizen science and how that'll shape the Clackamas River Basin. So yeah, more from Patrick. Bye all.
Thanks, everyone. Thanks again, Dave. Todd, appreciate it. I thought that went pretty well.
Awesome job.
Oh, thanks so much. Yep.
You're welcome. It did go very well.
Good. Thanks. All right. That's it. No one else has any questions? Dad, do you want to pop on and say hi? My dad is actually here.
That's great.
I don't know if he can. Oh, I don't think he can. Okay.
All right.
I'm going to watch the baseball game.
Okay.
See you,
Good night.
everyone. Good night.